Alright, should be making a video. Draftphysics.com, debatephysics.com also. Video presentation and such. I'm going to do a response to a Bruce Yeany video. Figured it'd be a nice Thanksgiving treat. Something like that. Holidays. So people who really don't involve themselves on the holidays, I figure they can have some place to go on the internet, whatever, and such. So Bruce Yeany hasn't been around for quite a while. I had emailed him a few times, trying to get him to understand that there's this subject of kinetic energy that isn't very well proven, and that maybe he should do some of these experiments. And unfortunately, he's chosen a Galilean style experiment, and but he's really not teasing the truth out of it. And so I just thought I would emphasize that fact that it's not a distant dependent force; it's a time dependent force. And there's no point in putting in your description, when you're talking about Galileo anyway, this falsehood of now called gravitational acceleration approximately 9.8 meters per second squared. That's not what Galileo discovered. There's no squared seconds nonsense that's involved in any way whatsoever. It's in clearly single timed units. Obviously Galileo didn't have seconds. Because he didn't even have a clock, frankly, a reliable ticking clock. And it's amazing how much time pieces evolved so quickly, after Galileo, late in Galileo's life, let's say, and, to the 1700s, an awful lot of progress was made in clock development. But, it's surprising how bad clocks were before Galileo. Anyway, so I think Galileo used a water clock. I think that's sort of written somewhere. And just counted the, drips of water, or, the amount of water that would go from one vessel to another, kind of thing. And that's all I need to point out. So this experiment, if described properly, it describes a lot of things properly. So if you get this one right, you get a lot of other things right. Now I should be able to, we'll see if this works. I should be able to actually draw on here. So if I had a river, and it was flowing, and it was a very powerful river, let's just say, so we're not going to worry about the fact that our relative speed will start to get close to the speed of the river eventually, so the river can't make us go any faster. Now obviously gravity, as most physicists know, is a speed of light force, so you're not going to challenge it by almost going the same speed, and therefore it can't give you much more. But I mean, the analogy would be exactly the same here. So if this ramp, he's just going to tilt it in gravity, and that's the same thing pretty much as just doing the same tilt in a river. And just say you had a floating ball that was being pushed by the river, it would do exactly the same thing when it hit a ramp. Okay, it would still being pushed by the river, and it would completely be time dependent. That is, the slope will slow it down more and more. So the more slope you create, the slower and slower the ball will move this direction, and the more it's sloped, the faster it will. And you're just really creating a way of forcing it to take more time, which means you're creating friction, all right, to slow it down. So technically you're using a lot more gravitational force, but you're getting across the river for that use of the force. The use of the force is giving you motion tangential to or perpendicular-ish, tangential I guess is safer, to the direction of the force. So the force is pushing you one way, and you're going to take some of that energy and move in the other way. And and friction is going to be the mechanism through which you accomplish that. So it's like every other time-dependent force. It wouldn't matter what kind of force I was using. Paint spray, I could be throwing a sandblaster, I could just be shooting spray of water, rain. All of those analogies work perfect to describe the circumstance of how we acquire our gravitational energy. And it's only momentum that we acquire. We only become heavy, okay? And heavy is the same thing as just moving sideways with a mass and a velocity. Momentum and weight are, in fact, the same thing. So, so I'll go through this. This video's got a lot of redundancy in it, and there's a lot of opportunity for him to explain that this force appears to be just like any other time-dependent force, like photons giving you a suntan. It's about how long you're in the sun. It doesn't matter what kind of moving around you do. It just matters how long you're in the sun. All right. And certainly any speed that, let's say the sunlight did give you speed and did push you, it wouldn't matter how much it pushes you. It's not going to change how much per second you're going to get of suntan, because you're never going to go anywhere near the speed of the photons that are hitting you. So, I mean, all of that science completely lost on these people. And that's how Galileo and Newton and Descartes were seeing things. They were seeing things as momentum. They weren't seeing things as any mv squared nonsense. That religion hadn't been invented yet, and that's all it is a religion. So anyway, so it is disappointing, okay, that he just won't, he won't do as he's told. Oh, obviously has no obligation to do that, but it's just disappointing that you can't get them to get to this core subject and take a position and argue it. I mean, the mv squared violates the law of the lever. It violates Newton's physics. It violates Galilean physics. Again, this mv squared, I mean, to sit there and put, to say 9.8 meters per second per squared is just such a lie. It's in 1 second units. And the unit doesn't matter. You could have it in half-second units, but then you have to change the 9.8. So the whole thing is just so irritating that they just, they just keep playing with this confused and sloppy crap, and they pretend that they're doing kids a favor, that they're teaching the subject correctly. They're not teaching physics. They're teaching nonsense. And, there's no nice way to say that. I mean, there's no nice way to say, oh, you're teaching it completely wrong. You're basically slandering Newton and Galileo and Descartes, and you're just misrepresenting the actual detectable truth, which is evil.
Hello, I'm Yeany, and today we're going to take a look at a demonstration that was designed by Galileo to help define acceleration.
So it wasn't a demonstration, obviously, for Galileo. The idea was to find some way to slow down the free fall velocity so you could actually see how something acquired its velocity. And so it slows the process down and makes it a lot more viewable or perceivable what's actually happening.
It was his testing of ideas like this that led him to be called the father of modern science.
Right, and you've all stomped on him. You all spit on him and, just push him into the dirt because you're misrepresenting what he discovered and how he discovered it. And so you're not standing on the shoulders of the giant. You're pissing on the giant, frankly. You're disposing of him like it was garbage. Like his physics wasn't right. His physics was right, and you've made a mess out of it. That's the simple truth. You've smeared your religion on his science. And the irony of the fact that he was being persecuted by people like you who have these fantasies and say they must be able to enforce their fantasy. They can force everybody to believe the fantasy. And if somebody doesn't believe their fantasy, they'll persecute them and just try to destroy them and do all kinds of doxing nonsense and other crap. Because they're malicious fanatics instead of people who love science and love the truth. They're afraid of the truth because if anybody speaks the truth, they treat them like garbage. That's the clear lesson here.
Now, we have built several tracks in the past, and I like them all, but this one's actually one of my favorites.
I don't really understand that, but whatever. It's the biggest anyway. Well, sort of. He has done a ton of this stuff, and it's all very redundant. And they don't teach the theory of any of this right either. So the simple lesson you learn from these different experiments where you change the two tracks and you compare them is that it's all about the velocity that the thing travels the distance at. So if you get it to travel its distance at a very low velocity, that is higher. So anything that's traveling at a higher altitude is going to go at a slower velocity. So anything that travels the distance at the slower velocity obviously will take longer to get to the other side than something for which you allow it to gain its full velocity and travel at its full velocity. Because at its full velocity it has less friction, all right, and it's also traveling faster, so it's clearly going to get to the end sooner. And that's what the simple lesson here is, that you're allowing it to, you're turning its potential energy, the fake notion, into kinetic energy, and you do it for a bigger part of the voyage. Obviously, the more velocity you have for the longer part of the trip, the better off you'll be. If you're going slow for most of the trip, it's going to be a very long trip.
Here's some of the other tracks we've built. I'll put links to them down in the comments below. This piece has two identical tracks. I can release the balls at any location and they'll still reach the bottom together.
But you won't be able to see that probably because it's too short.
This track helped Galileo design the idea of inertia.
So again, there's no idea of inertia. There's just the fact that something needs to have energy to move. And so it doesn't demonstrate anything called inertia. So I don't know why he says that's an inertia demonstrator, when again it's just demonstrating that the quicker you get out of the gravity, the quicker you got out of the gravity.
There are several varieties of high-low tracks. Here's one of them. I've tried adding humps to the tracks.
See, the one ball, the top one, it's very low. You know, it's all traveling the same height. And so it never gets its maximum velocity. It's always traveling slower. So you could just have it at a lower track and it'll beat the other ball. So this is all stuff you can just fudge. But the idea is that obviously you gain momentum by allowing gravity to do positive work, that is, push you down. And if you push yourself back up again, well, you lost what you gained. Duh.
I've also made them larger. And here's a track that helps explain pendulums.
So I don't think it really explains anything. That's the point. And especially if you're still arguing that there's some sort of 9.8 meters per second squared thing involved, then you're really not teaching gravity accurately, because there's no squared function.
All these pieces were influenced by the work of Galileo.
Now, Galileo easily could have had a wooden track made that a metal ball could roll down it. His problem, however, would have been trying to time it.
Since stopwatches weren't available,
Yeah, but you can just visually see it, so you don't really, it's almost like you don't need to time it to get it. But obviously to get anything precise, he needed to time it. But I'm sure he got the idea pretty quick that it's in units of time. And that's what he discovered. It's in units of time. It's a time-dependent force.
Galileo would have had to figure out other ways to time his experiments, such as using his pulse,
3, 2, 1.
perhaps using a pendulum. Another possibility is he could have used a stream of water.
Well, like I said, I think it's in the records there somewhere that he talks about the water clock, so I think that would be the obvious. I think that's what he used.
Start. Stop. The amount of captured water could be measured as a passage of time. I want to start this experiment by dividing the track into 5 equal parts, and each segment's going to be 28 inches long. I've angled the track so it takes about 5 seconds for the ball to reach the bottom.
So he does this over and over and over, so the video is kind of disappointing in that respect.
We're going to start by measuring the bottom segment for time using that water clock. Here's our...
So, you know, he's measuring time based on shorter and shorter distances. So it's not going to tell you that they're obviously not going to be the same. So if he measured it in 1, 3, 5, 7 units of distance, then you'll get the same time.
First measurement. Now we'll measure it for twice as far. Due to that it's accelerating, it's not quite twice the time. Here's a measurement for 3 times the distance.
Now 4 should be twice the time, and it looks a little bit off, but that could just be the camera angle.
4 times the distance.
So 4 times the distance should be twice the time. So he doesn't give us the measurement, so it does look about right. You know, that would be twice the fluid. So, but it should be easy to see that, right? So I guess I have a ruler here somewhere. Yeah, I certainly could put that on top of it, I guess. Yeah. So yeah, it does look like it's more, this is a little bit fudged. That looks a little like it's not quite. That's a little twice as much, a little more than twice as much. So I guess I could just say, let's see. Yeah, this space is the same as that. Yeah, this white space here does look bigger. So, but whatever. Not terribly important. Close enough. But he doesn't say anything about that. That twice the distance, 4 times the distance is going to be twice the time. And that's really the most important thing you can say, is that it comes in units of time. It's going to be twice the velocity.
And here's the whole distance.
So the whole distance isn't one of those even numbers, so it's not going to be very helpful.
So while the distance between each release was the same, we can see the time gap gets shorter as the ball picks up speed going down the track.
So again, it's the opposite. You started slower. That's the whole point. It's not that it's going slower, it's just going uphill, but it would do the same thing going uphill. If we have the same proportions, you'll lose your velocity the same way. You'll lose a little tiny bit of velocity, but you'll take a long time doing it at the end. And you'll lose a lot of velocity and take very little time to do it in the beginning, going up against gravity. And obviously it's the same way gaining your acceleration. So in the first second, or the first unit of time, well, let's just say second, you'd only do that 4.9 units of distance. You don't get 9.8. And so if you drew all that out on this stupid chart, it'd be clearly obvious that, yes, you're just adding velocity. This isn't about acceleration. The acceleration is at 1 unit of distance and 1 unit of acceleration per section of time. So in the first section you get 1 unit plus 1 unit of acceleration. The next second you get 1 unit of distance, 1 unit of acceleration. In the third second you get 1 unit of distance, 1 unit of acceleration. That's what he should be explaining. And just like every other time-dependent, any other force you could apply to something to change its motion, rain or sand or paint or whatever you're spraying at something or spraying on something, it's exactly the same kind of time dependency. It'll obey the same rules. So gravity is just like all those other ways of applying a force. And instead of saying that, because they want to keep it a mystical pull thing, they don't want to imply that it's a push force like spray paint. But it is. It works exactly the same way as a spray of paint. The slower you take to go through the paint, the more paint you'll get on you. And the faster you go, the less paint you'll get on you. And this works exactly the same way.
Tested each position several times and found I got pretty good results.
Now, another way we can demonstrate this is to put bells equal distance.
So that's what Galileo actually did. So this is duplicating Galileo's experiment.
Distance along the track.
Once again, it's the same 28 inches in between each mark.
He didn't bother with that, I don't think. He tried to figure out what the unit of distance was that would be the same time. But anyway, continuing.
As the ball rolls down, we can listen to the intervals in between each ring.
can hear that the rings get closer as the ball speeds up.
Yes, it's gaining velocity. So each second it gains, and he says it takes 5 seconds. Each second it gains 1 unit of acceleration. So it's going that much faster, 9.8 meters per second faster, and then 9.8, and then 9.8 each second. So by the end it's going, whatever, 50.
We'll try it again with the ramp steeper.
So this doesn't help at all. I mean, it's just it just makes it happen faster. So, I mean, happening faster isn't very interesting.
With these types of measurements, Galileo determined that when a ball is released from the same point, the distance it travels will be proportional to the square of the time.
Right, and because it's time dependent in the first place, and it's accruing velocity, so it's getting free distance. So every time it got 9.8 this first time. So, you know, if this isn't really drawn to scale, frankly. But anyway, yeah, because this one should be, no, that's way too much. This doesn't look like twice the distance, frankly. But anyway, so this is twice the velocity. So it should be 4 units in here. But the fact is that after the first unit of distance, all right, you have the 9.8. So then you're going to get 2 full units of distance for free. And then you're going to add your 1 more 4.8. And that's how it's going to continue. You're going to go 1 unit of distance, then you're going to go 3 units of distance, then you're going to have another free unit added plus the extra velocity you added, and so it goes, 5, 7, all the odd numbers.
So if the time is doubled, it travels 4 times further.
So yes.
There.
And I guess I could draw that. I mean, it's just not that, what do I do with my pen? Can't be very far. Yeah, it's not very far. Didn't think it could be very far. So look, the simple argument again is, let's see, where am I? Up here? How come that's not showing up on there? Actually, that's because this is above that. So I have to move this camera up. That should get me up high enough. Okay, now it should be, I can draw on anything here. It should just show my little dot, but it doesn't. Dot's too high. No, it doesn't show that one either. It doesn't show that one either. How come that isn't working? It works down here. Okay, so there's a reason why it's not. Oh, it's turning white. That's why it's not showing. It's white on white. I can't do white on white. Alright, so I can't draw on there. But the simple point is that you have this length of line, and the fact is you do this tiny little distance in the first unit of time. Then you're going to get 2 of those for free, and then you're just going to add 1 more in the second. So each time you only get this little hunk of distance. This is all you ever get. Each unit of time you just get this distance. The rest of the distance is all for free by your accrued velocity. So that's all you're getting. You're getting the same increase in your velocity per second and the same increase in distance per second, and the rest is all the velocity you've already acquired. So the velocity you've already acquired is doing all the rest of the work, so to speak, if it was work. Just falling isn't work, so you're not doing any work. But it really is exactly the same thing you're getting each unit of time. The same amount of rain is hitting you. No matter how fast you go, okay, you're still in a unit of time going to get the same amount of rain because the rain is coming at a timed rate. There's a certain amount of it coming per second, and it doesn't matter whether you're going this way or you're going this way or you're going that way. It doesn't matter which way you're moving. It matters how much time are you in the force. That's all that matters. It's how long you're in the river will decide how much momentum the river gives you.
If the time is tripled, it travels 9 times further. This proportion continues for any object under constant acceleration.
If you're on the moon, it continues. If you're on Earth, obviously the atmosphere is going to get in the way and you're not going to be able to go any faster. So again, this formula, S equals 1/2 AT squared, could just be converted. You don't need the A. It's just a matter of understanding that it's the time component that is the square root of.
The behavior follows this formula. With the track at the original angle,
So this I can use to my advantage, to point out the obvious that he should be pointing out. Okay, so you get 5 inches is going to be the same as 5 meters in a real experiment with 1 second units. So because of the huge slope he has, in terms of the force, he's almost perpendicular to the force, so that's why this is so slow. But yes, it's very good that it comes out to these 5 units. Okay, and that's all you're going to get as a distance in the first second. And the fact is, that's all you're going to add in the second second.
for the first second, the ball is going to travel 5 inches. In 2 seconds, it's going to go 4 times.
So he could show that visually more exactly, okay, in terms of recognizing that you're going to go this 5 inches, and then so gravity just gave you this extra velocity, so that's going to give you 2 units of motion for free, and then you're going to get one more 5 inches.
Times further, or 20 inches. In 3 seconds, it's going 9 times further, or 45 inches.
And again, so it's just because you're always adding to the previous distance in terms of your free velocity. So second, you're going 19.6. So obviously if you got 2 units of free velocity, now you got 4 units plus your 1 extra, so that's 5.
In 4 seconds, it's going 16 times further, or 80 inches. And finally, the whole track will take 5 seconds. The ball will go 25 times further than it did in the first second, which is 125 inches.
Right, so he's implying, like I said, this sort of implies that this is somehow, and all you got in that last second, all you got was the same amount of distance for free, but from gravity, and the same amount of acceleration. All of the rest was the velocity you already acquired.
So now we have the distances stretched out.
So, as I would argue, let's see, I should be able to draw on that. Let's see. Where's my pen? Okay, it's way up there. Yeah, I gotta go down. That's the problem. I can't see it. So I can't really draw the units in the right proportions. But this is what you're going to gain, is 1, 3, 5, and then 7 and 9. In terms of the distance you're going to acquire. So yeah, I think I'm not going to replay it. But this should have been 3 units of distance, not 4 units of distance, this second hunk. It's 1, 3, 5, not 1, 4, 8. Yeah, whatever. Anyway.
But the time in between each...
I have to erase that, don't I? Well, I don't have to. So now he's just going to redo this over and over and over from different heights, so it's not going to be very interesting.
Each mark is the same.
There we go. So at least now he has the marks, and then he's going to put the bells there, and then you'll get the same sound for each, indicating again that it looks like somehow gravity's giving you more the longer you fall, and it's not giving you more. It's just giving you exactly the same in a unit of time. Again, how many times you have to say it? It's not a distant dependent force, it's a time dependent force.
So now if we put the bells back on, if I roll the ball down the ramp, we should hear equal intervals in between each ring. Now if I have this set up right, it should be about 1 second in between each location. Let's give it a try.
So he could have had a clock or something running next to it, and then you could see that, yes, that's how it worked out, but whatever.
Let's go back and listen to the equal distances, where we hear the time intervals speed up.
So I think
And
it
here
would
again
be,
is where the times are equal.
it would be better just to focus on this experiment where you're showing that it's coming in units of time. And you're only gaining the same little bit, okay, each unit of time.
Try it again with the ramp steep.
It's the only part that you had to add.
Steeper yet for the equal distances.
So this, like I said, comparing these two just makes noise. The point is that it's not about the distances. That's clearly where you don't have you're not having a constant force of being applied, because you're getting inconstant rings of the bell. So the constant force is described by the equal amounts of hitting the bell, and that's the one that's showing time dependency. And it should be emphasized. It's really important. The fact that it's time dependent ties it to all the other pushing forces. So I'm just saying, any other force you can imagine that's discrete or in little bits, and it pushes something, it's going to do it exactly like this. Exactly, you could duplicate this experiment in that field. In that, I can duplicate this in a paint spray. I could duplicate this in a sandblaster. I could duplicate it in a wind tunnel.
Compare it to the equal times. Let's go higher yet for equal distance.
So again, just keeps doing equal distance, equal times, and you're just confusing the subject. The subject is that equal times is how you're acquiring the force. You're acquiring the same increase in your velocity per unit of time, not an increase per unit of distance. And you're not gaining any squared amount of acceleration, so there should be no squared on any units.
And once
more,
again,
higher
for the
yet.
equal times.
I think it's pretty amazing what Galileo was able to accomplish, considering what he had to work with.
Right, and it's just amazing how you've all dumped on it and ruined all of it, and all the value of it's been thrown away by this nonsense mv squared BS invented by Leibniz. Just completely ruined physics.
Anyway, I hope you enjoyed this video, and thank you for watching. Okay.
I haven't measured the weight of an electron right, because you used your silly religion instead of Newton's physics. If you would have used Newton's physics, if you would have used momentum to measure its weight, you would have got a completely different weight. Well, lots of ways you've ruined your own science with this fable, this easily proven irrelevant fable that can never be collected and never does any work. It never successfully accomplishes anything, ever, and yet you keep selling it.
Okay, bye.
Whatever. Okay, so just kind of annoying. I'm disappointed that he's sort of doing a video on the subject, but he's not emphasizing the important fact that this isn't a distant dependent force. You acquire it in units of time. That's what he just proved, but he didn't say it. You know, and that's the annoying part. Didn't acknowledge it. Alright, so I guess Thanksgiving isn't a great time to do a video. Only 3 viewers, so that's kind of thin. Yeah, so I guess I don't have to hang around too long. But we'll see. See what I feel like doing. I guess I could put the chat in here, and then I could draw on top of the chat because it's pretty dark, or something like that. And I guess I could re-illustrate all of this crap. But again, it's it's just so obvious that in the first second this is what you get, and then in the second second you're going to get this plus the one more from gravity. So I'll just put a little arrow indicating this is the one from gravity. You don't have any velocity, all you get is this from gravity. Then in the next second, this is the only one you get from gravity. And then in the next second, that's the 3. So you have the 1, you have the 3. So that's 1 plus 3 plus 1 is 4. So in 2 seconds you got 4 units of distance. That's the squared part, but it doesn't mean much. And then you're going to add, because you've increased the velocity twice, you've doubled it now. So now you're going to get 4 free ones. So it would be 4, if you could see it, 4 free units of distance. And then 1 extra for the 5. 1, 3, 5. And it just keeps going like that. So you're only adding this each time. That's all you're adding is distance from gravity. And all you're getting is that increase in your velocity. But obviously the increase in the velocity always ends up making your velocity increase by that extra 2 units for every increase in the number. But so again, it's twice the velocity. I wonder if this pen will actually show up. So if you compare it to the 1 unit of distance, this is only 2 units of time. Alright, and you only have twice the velocity when you land. So yes, it looks like a lot. Oh, it's dropped 4 units of distance. It must have a lot more energy. No, it's got only 2 units of energy. This one has 1 unit of energy, just like this. And you're going 1/2 your velocity here. Okay. I mean, that should be the huge giveaway, right? I'm going half my velocity after just 1/4 of the trip. So obviously I must not be doing any collecting of gravity here in any kind of the same proportions, right? I'm going much more distance, but I'm only getting this one little notch of gravity. And the obvious answer is, as I pointed it out, it's because the gravity is only doing that 1 unit of distance and that 1 unit of extra velocity. It's pushing you the same, but you're moving through it faster. And how fast you move through it doesn't change how much it's pushing. So it's going to add the same extra motion, and it's because it's doing the same thing each unit of time. And the only thing you're changing is keep gaining more and more velocity. So a bunch of this distance you travel without being pushed. Look, if you go the first unit of distance, and if I could shut gravity off, you're still going to go these 2 units for free. With gravity turned off, you're still going to do that. So if I was pushing you with paint spray, the same thing would happen. Once I gave you 9.8 meters of velocity, you're going to keep it. So you're going to go 2 full units of distance in the next second without being pushed anymore. And you're going to keep doing those 2 units. You're going to retain that velocity. And it's just so obvious. There's no room for any notion that you're getting 4 units of gravity here. You can't get 4 units of gravity because you're only in the force 2 units of time. Oh, how many times do I have to say this stuff? No point in asking the question, I guess. Just to press you, Gary. True enough. Alright, so where was I? This one here, I guess I could change that to this. Yeah, I did accomplish that. Alright, so no commenters yet. Oh, we're down to 1 viewer. Yeah, so it's no chance we're going to get any commenters, I guess. Alright, so I probably won't I probably won't stay very long then. Really no point. Yes. Very much no point. Yeah, I'll just make it a video and say, have a nice day. Yeah. So I guess there aren't too many people who don't have some silly distraction on Thanksgiving to have to deal with some sort of family crap. Yes. Yes, thankfully I'm not such burdened. Alright, so anyway, till the next time and such and so forth and whatnot. Let's see, which one do I want to hit? Guess I might as well use this here button. One viewer. Yeah, that's pretty funny. Yeah, one. Well, it's not 0. Yeah, okay, true enough. It's not 0.